All right. So what we're going to do this week, we finished our lecture last week with a couple minutes ahead of time. And so what we're going to do today is we're going to start talking about visual acuity. So again, we're going to talk about visual acuity today. An alternative title for this lecture, I suppose, is more about visual acuity than you probably wanted to know, but probably need to know for boards and contrast. So not just visual acuity, but contrast today. Lecture title suggestions would be appreciated. So just let me know after class. Thank you, Neil. So let's talk real quick about visual acuity. I try to keep things up to date somewhat with relevant research or relative news articles, that sort of thing, that pertain to low vision or pertain to things that we're talking about. And so what you can see here is this paper, this research that was performed, is talking about visual acuity and contrast. Now, so how many people in here have checked visual acuity on a patient? Everyone, right? Not you, Ainsley? You haven't checked any? Maybe one. Everyone? Okay. Okay. That was just a check to see how many people would actually raise their hands. It's more than anything. So everyone here has checked visual acuity on a patient before, right? How many people in here have checked contrast on a patient? Show of hands. Couple? Okay. Are we being honest or not? I mean, not the ones that raised their hands, but the ones that didn't raise their hands. Or have you never checked contrast acuity on a patient?
Not intentionally.
How did you check someone unintentionally?
I know what you do near acuities in the dark.
Exactly. Yeah.
Oh,
That's contrast.
that is true. Yeah, actually, that would probably be a really good test. So, how many letters can you read? I'm sorry.
You like accidentally hit and the contrast lower.
Yeah. So the Acuity Pro or whatever we've got here in our clinic has a button to change the contrast and decrease it a certain number of levels, that sort of thing. So as you know, kind of seen by showing of hands, contrast is not something that's checked very often, but as this paper suggests, is actually very important, and it's probably a test that is under checked or I guess should be checked more, for lack of I can't think of another way to describe that. So let's start off here with the question. Now, don't skip ahead in the slides. But what I really want you to think about and what I want you to tell me is, what is visual acuity?
The smallest, well,
What you got, Paige? I saw you snickering over there. What you got?
What? I said the smallest foot size that you can distinguish on a chart.
Okay.
Yeah, good answer.
Good answer. Good answer. Good answer, right? Okay. Anybody else? What is visual acuity?
retinal resolution.
Retinal resolution. Okay. Is there any specific spot of the retina that we are assessing when we're doing visual acuity?
Oh, yeah.
Macular fovea, central visual acuity. Yeah, central resolution. Exactly right. Most of the time, and I recognize that we do visual fields and that sort of thing, but most of the time we're not checking the peripheral visual acuity or peripheral sensitivity on a normal patient, other than just to see, you know, can you see this bright light coming in, or can you tell me how many fingers in each quadrant, that sort of thing. So as I mentioned, as some of you said, visual acuity is typically checking the central retina, and this is typically a high contrast measurement. Okay, so except for accidental trying to have a patient read a near visual acuity in the dark or something like that, we typically will leave the lights all the way on, or we'll have the monitor on, or we're using cards that are almost pure white and pure black. So it's typically 100% contrast. Although, as we've kind of talked about before, and you may have talked about back in vision science too, this is not a real world situation, right? There's a lot of artificial things related to visual acuity whenever we're measuring it in our office. So, you know, from a medical legal perspective, it's important to check that sort of thing. Typically, the kind of visual acuity that we are doing is resolution acuity. So think back, dig deep, vision science 2. What are the other two types of visual acuity that you learned about?
Vernier.
Vernier and
Minimum detectable.
minimum detectable. Yeah, exactly right. And so if you can't remember those, or if you didn't, then brush up on those. Of course, again, in low vision, we're not going to check either of those either. We're also going to use recognition acuity. Resolution acuity. So in that regard, remember that we may have patients that are illiterate or can't see letters, that sort of thing. And so, of course, we do have the ability of having matching charts and other options for those patients. The visual fraction that we use, the 20 over whatever, what does that indicate?
This foot size of the related.
The foot size of the letter. Okay, yeah, you're exactly right. So if I say your patient saw 20/20, what does that mean?
This one argument, 120.
The letters.
So hearing lots of similar things, but at 20 feet, that optotype that the patient read subtended an overall arc of how much? The whole letter. 5, and the details subtended
1.
Very good. Excellent. So this, what you just talked about, is the overall letter size is the angle of resolution. Now, these lines and spaces are what allow us to see the letter as separate. And so you can see here that we have different letters, and you don't really think about the optotypes much, but the actual makeup of the letter is such that the width of the bar and the width of the spaces subtend 1 minute of arc apiece. And so the overall size of the letter then, in this case, is 5 minutes of arc. So the minimum angle of resolution are the actual bars and spaces. So the actual strokes or the spaces between the letters. And this is the minimum angle that we can typically see, or as the name implies, the minimum angle of resolution. So we typically try to assess, and at this point, probably in your optometric career, maybe when you first started, you were trying to push your patients down as low as they could go. Let's see if we could see 2015 or 2010. They were still reading letters. At this point, once they hit 2020, we're done. You know, we don't typically press them any further. So I wouldn't say that this is 100% accurate, that most people can see 2020 only. However, that's the letter size that we're always shooting for. So what about, let's ask about a couple other things. We talked about 2020. We know that the overall height of that letter at 20 feet is 5 minutes of arc, or rather the angle that letter subtends at 20 feet is 5 minutes of arc. I may have said seconds there, that's my fault. 5 minutes of arc. So if we have a 2400 size optotype, what is that letter or that optotype's overall height if that letter is at 400 feet? 5 minutes of arc. Yeah, so the relation between the letter and the 5 minutes of arc is just that. So if it's a 400-foot letter, if you move that letter all the way out to 400 feet, then it would subtend 5 minutes of arc. If you have a 20-foot letter, then at 20 feet, it subtends 5 minutes of arc at 20 feet. 40-foot letter, 40 feet, and so on and so forth. But as you can probably imagine, it would be sort of superfluous, I guess, or really not worth your time to take a 400-foot letter and move it all the way up to 400 feet, because all you'd be able to check then is, again, that same kind of 20/20 acuity. It would be 400 over 400 in that particular case, but it would be fairly worthless. So what we typically do is we move our letters closer than their actual foot letter would indicate. So for instance, in our clinics, I'm getting ahead of myself a little bit. In our clinics, even here at NSU and over at Cherokee Nation, the charts are not set at 20 feet. You know, they're typically 10 feet, maybe even in some cases just a little closer. And so we have to therefore calibrate our computers and calibrate the letter size in order to make that letter the right size. We have to calibrate it in order to make it correct. But I'm getting a little ahead of myself, so let me scoot forward just a bit. So originally, whenever Snellen was first used, we would try to put the chart at 20 feet, and therefore a 20-foot letter was subtending 5 minutes of arc at that distance, just like the chart implies. Today, we don't really do that, although we still use that nomenclature 20 over X, 20 over 80, 20 over 20, something like that, even though our chart is at maybe 10 feet or 12 feet, something like that. In reality, if we were still using the same style of chart, but we had moved it closer, then what we would have to do is separate the optotype size from the distance. And so instead of saying that this is a 20/20 letter or something like that, what we would look at is the optotype size, what it had printed on the side of the chart, and then we would just put the distance in front of it. So if the chart was set at 10 feet and the patient read a 12-foot letter, then the acuity would be 10 over 12-foot letter, or 10 over 12 feet. Now you can probably in your head double this and make it a Snellen equivalent or a 20 over X equivalent optotype. And that's often what we do in low vision. So you can see here a couple of examples. A 12/12 letter, a 12-foot letter seen at 12 feet is still equivalent because of the angle of resolution to a 20/20 letter. A 14/28 foot letter size. So the chart in this case was held at 14 feet. The patient read a 28 size foot letter. And so in that case, the equivalent would be 14/28. And this, if you then switched it back into a Snellen format, would be 20/40 in that case. So all I'm trying to explain to you is that whenever you're assigning these specific visual acuities, they have an intrinsic meaning. Now in low vision, we do typically take and convert our acuities to Snellen, but that's just typically for the general public to see. Most of the acuities that we use in low vision, the native formats are M acuities, and we'll talk about that here in just a second. So I did some examples here just to kind of prove to you, and just to show you, you may have seen this table before, but just to show you what the relationship is between the visual acuity and the MAR and then the overall angular size, or the overall optotype angular size. So if the letter is a 40-foot letter and it's held at 20 feet, then all you have to do is divide 40 by 20 to come up with the MAR. And then you multiply that MAR times 5, and that's the overall optotype size. Have you all seen this before? Okay, perfect. Then I'll move on pretty quick. You can look through the rest of these at your leisure, and just to understand what's going on here. But I want to kind of start talking about M acuities. And sometimes these are a little bit scary because maybe you haven't used them a lot. You're probably familiar with them, but you may not have used them a whole lot. So I want to start establishing the relationship between this MAR and overall angular size to the M acuities, just to prove that Snellen and M acuities can be, they are basically intrinsically the same in terms of MAR and overall angular size of that optotype. So this is just showing that there's lots of different ways that you can represent visual acuities. So sometimes papers will display acuities in decimal format, but more typically they'll display them in terms of logmar. So in logmar format. These are just a couple of different ways that they can be represented on a paper. We don't really do this a whole lot in low vision. I just wanted you to have access to this information so you can reference it there if you need to. So let's talk about crowding real quick, because as we'll discuss, one of the things, the charts that we use in clinic are really, really good quality charts. But before we get to that, and before we get to M acuities, let's talk about crowding just a little bit. So looking over here on the left, we have a pretty common paper version of the Snellen chart. And you can see here that there are, as we move down the chart, the first letter at the top is a 2200 letter. And then you can see that there's only one letter at the top. And then as we move our way down the chart, you can see that we increase the number of letters. What this represents is some unequal spacing. And as you already know, for certain amblyopes, if you show them isolated letters with no crowding bars or no other letters around it, then they'll typically have a better visual acuity. But this isn't necessarily representative of their true visual acuity. So we always recommend that you use crowding bars if you suspect that your patient is an amblyope. On the other hand, if you use a chart over here, like so, as long as the patient continues to read letters that are within the lines, then it's already got crowding built in. Now, if they read isolated letters on the outsides and they just bounce from one outside to the other, or from one end of each line to the other, then of course that could represent or make the acuity easier, make the letters easier to see, and therefore overestimate their acuity. So we do have to make sure that the patient reads each letter on the line. So this is the Snellen chart, and I didn't want to give too much away before, may have given a little bit away. But this is a very similar chart to what you see hanging up at CNOC, and I think we've got a couple downstairs. Just if your horrible attending asks you to do trial frame out in the hallway, then this is the chart that the patient is looking at. So what are the advantages and disadvantages of your classic Snellen chart? Quick and easy. Okay, so that's an advantage, I would think. Okay. Jim says quick and easy, so that's an advantage. What are some other advantages?
It's universally known.
Familiar, very familiar. Yeah. What else? What are some disadvantages? We talked about advantages, a couple of those. Letters aren't equally spaced, that's correct. What else?
Doesn't test contrast.
Hey, there you go. Yeah, a gold star for you. Yes, you're right. Doesn't check contrast. That's absolutely certain. So there's a few other things that you can see. We just talked about crowding, and so there's somewhat unequal crowding of the letters as you work your way down the chart. The other thing that you're going to see is that there's uneven spacing between the letters. So you can see here that this chart is very nice and uniform in terms of, it keeps all the letters, real close to about the same width overall in terms of the line. And so what that means is that the spacing between the letters is changing as you're working your way down the chart. They're increasing the number of letters per line, that sort of thing. The other thing that can sometimes throw folks off are these serifs that are on the letters. And so you can see here, like the T, for instance, those little extra ticks on either side of the crossbar at the top and then at the bottom. So those things can sometimes throw patients off just a little bit because they can sometimes confuse them for other letters. Yes.
What's the purpose of the red and green lines?
So that kind of gives you a representation of, I don't know why they would put red down here, except for maybe the fact if you're trying to refract the patient, maybe perhaps they could see the red a little clearer. Maybe they indicate they were over minus. Green is a little clearer over minus, red is a little clearer over plus. It also gives you a quick reference because in this case, at least the lines that are between the two are 2025, 2020. And so maybe red means stop, quit wasting your time, don't push the patient any further, or something like that. But truth be told, I don't know 100% what those are for. Here's another thing that comes up sometimes in clinic. So you're doing an exam on a patient, and this could even be the Acuity Pro. So I know that I've got classic examples of the Snellen chart up here, but just think to your Acuity Pro. And imagine that this is your patient that you're doing Acuity on. What's their Acuity?
20/30 minus 2.
20/30 minus 2, huh?
Just 20/30.
20.
Answer.
Well, how do you account for the letters that they missed on the 2070, 2050, and 2040 lines?
Chance.
Dyslexia.
Chance. Okay, but you can't record their acuity then
Oh,
correctly,
okay.
right? You can't account for those letters that were missed. Would we agree on that?
Yes.
Okay, so does it matter?
No. It depends.
I'm going to shrug my shoulders a little bit and say perhaps. If you're doing a research paper, it absolutely matters. If you are, in our case in low vision, we want to try to be as precise as we can because our patients' visual acuity can fluctuate a lot from time to time. And so we do want to be accurate. And in that regard, Snellen sometimes comes up a little bit lacking because, like all of you, I would probably say this patient's visual acuity is 20/30 minus 2. But knowing what I know now and what you all are about to know about visual acuity, that's not accurate because they missed letters on their way down the chart. Now, if all we care about is like the central visual acuity and what's the smallest absolute letter that they could read, well, then they got a couple letters on the 2025 line. And so therefore you could kind of arguably say, well, their acuity is, in some cases, 2025, maybe just a hair worse than that. But we would never record it that way because they didn't get the majority of those letters correct. So if we're going to take off letters from here, then in this case, then why don't we account for the other letters up here? That's more of a philosophical question, I suppose. So a chart was produced, or a chart was introduced to kind of take, what am I trying to say? A chart was created to try to account for some of these Snellen chart weaknesses, to improve upon the chart, to make it a little bit more uniform, and therefore make our visual acuity measurements a little bit more accurate. Now, again, truth be told, we try to do this in low vision. We try to be as accurate as we possibly can because we're dealing with patients whose visual acuity is poor, of course, and we're wanting to make sure that it's not getting any worse. The first chart that was introduced with a logarithmic optotype size progression, meaning a uniform progression down the chart, was the Bailey-Lovie chart. Then the early treatment of diabetic retinopathy study came along, and they took that chart and they improved upon it. Now, there's some other stats that you can see down here. So it's got Sloan letters, for instance. And so you can see here approximately some of these letters that are used. The other things that it's got going for it are the optotypes are square and their width is equal to their height. And then again, just like before, that stroke width or the bar itself is equal to the MAR. And that's nothing new there. It's just the same with this ETDRS chart. As I mentioned before, with the ETDRS chart, each optotype is 5 by 5, meaning that the height or the horizontal and vertical distances are the same. The spacing between the letters is also the same. So it's also in this case 5 by 5. Then the distance between each line, and so if you can see the lines here, is equivalent to the height of the next line down. So in the case here, the second line down, this height here between the C and the S is going to be the same height as the S. Hopefully that's not too confusing. The way the chart is built in that it has 5 letters on each line, you can see that it sort of makes a triangle as we're working our way down the chart because it maintains 5 letters. It doesn't go, well, we want it to be nice and neat, you know, good columns on either side. It instead says 5 letters on every single line. And as we make our way down the chart or the lines are just going to get shorter and shorter and shorter because the optotype size is decreasing. As I mentioned before, the Bailey-Levy chart was the first one that had uniform logarithmic progression in letter size as you work your way down the chart. The ETDRS borrowed that progression, and every single line on the ETDRS chart is 0.1 logmar smaller than the one above. This just indicates that you have a very uniform progression of your letters. Now, we use this in low vision all the time, and there is a version of this that's on the Acuity Pro, on the Acuity Pro, so you just have to find that in the options. Logmar is what we're going to learn. We're going to talk about that today. We're going to learn how to calculate that today. But just so that you know, Logmar is not typically used in clinic. It's almost always exclusively in research papers, that sort of thing, just so that we can be very, very precise, or researchers can be very, very precise in determining if a medicine of some sort or treatment is improving or making a patient's vision worse. This graph here is just showing you letters and the uniform progression of the Bailey-Levy chart relative to the Snellen. And remember, ETDRS borrowed the Bailey-Levy chart, borrowed its logarithmic progression in order to make its chart. And therefore, it would fall under similar, or it would look similar when compared to the Snellen acuity charts. So we've talked about Snellen, and we've talked about how if the chart was set correctly, you know, if it was a real 40-foot letter, and it was seen at 40 feet, then the overall angular subtense of that letter, the whole letter, would be 5 minutes of arc. If it's moved half the distance, if it's moved up to 20 feet in that case, then the overall angular subtense of that letter is going to be 10 minutes of arc, and the MAR would be 2 minutes of arc. So let's talk about M notation just a little bit. Because with M notation, probably the best thing about it is that you don't have to think. So who enjoys that? In your visual, in your exams, you don't have to worry about anything. You don't have to try to convert anything in your head. All you do with M notation is the first thing you do is you write down the distance the chart was at. If the chart was at 3 meters, you write 3. If the chart was at 4 meters, you write 4. If the chart was at 1 meter, you write 1. Good job. Yeah, you're seeing the trend there. Excellent. The second thing that you will write is the optotype that the patient read. You don't have to do any conversion. You just take it directly from the chart. And if they read the 6.4M optotype or the 8M optotype or the 20M optotype or whatever it is, whatever letter size that they were able to read, you just write that number second. And that's all you do. And then you put an M after it and you're done. You don't have to do anything else. There's no conversion or anything. All you do, distance first, optotype size that was read second. So with that in mind, let's imagine that you are in the clinic. You start with your chart at 3 meters. All right. So your chart is sitting all the way at 3 meters and your patient read the 25M line. What are you going to record?
325M.
3 over 25M. Exactly right. Okay. So that was with their right eye, for instance. Left eye, much poorer vision. So you move the chart up. In this case, you put the chart at 1 meter, and guess what? The patient reads the 25M line again. What are you going to record now? You just move that chart up 3 times closer.
1 over 25M.
Great job. I thought I could trick you, but I couldn't. So very, very good. You're exactly right. And now if we do the math on that, and if we do the Snellen acuity, and we convert 3 over 25M, which would be like 20 over 167, and we convert 1/25m, which would be 2500, what we would see, I guess what we would see there is that the optotype size, we move the chart up ×3, and therefore our Snellen acuity got 3 times worse. Okay? So the point is that I'm trying to make is that you don't do any conversion. I see students fall in this trap all the time of thinking, well, I moved the chart up 3 times closer, therefore I've got to multiply the optotype size ×3. But that is incorrect. You just write the distance, you write the optotype, and you're done. You don't have to do anything extra. Capiche? All right, let's move on here. Let's see. Now, on certain charts, know that it does say something at the top. It says chart is calibrated for 4 meters. I've already just told you that M acuity is so simple. All you got to do is write down the distance and write down the optotype. And now I'm throwing a wrench in there and saying that some charts say 4 meter 4 meter calibrated distance. So these same charts will have lists of numbers on either side, and they'll have logmar, they'll have decimal, they'll have Snellen acuity, and that Snellen acuity is the one that can throw us off just a little bit, because what that conversion or what that calibration means is that at 4 meters, then whatever the Snellen acuity that's listed on the side is accurate. But we don't like to use the Snellen acuities just because we are moving that chart a lot during the exam. So we might start off at 4 meters or 3 meters in these new rooms that we've got, and we have to move it up to 2 or move it to 1. So we don't like to look at the Snellen acuity because that number that's listed under Snellen acuity is only valid at the distance that's on that chart. So if the chart says calibrated for 4 meters, that means the Snellen acuities on the side are calibrated at 4 meters, okay? That's the only time that you could use them. Otherwise, you need to use the M acuities. And again, all you got to do, distance, optotype, and M, done. And then you can convert to Snellen if you need to for papers, for notes back to other doctors, that sort of thing. All right, so let's go through these real quick. I think y'all are going to be pros at this point since we've already kind of done a couple of examples. But what would your acuity be for a patient who read the 6.3M letter size and the chart was at 4 meters?
6.3M.
Very good. What about this last one? We'll skip the second one. No, let's do the second one since it's a different distance. Patient read the 10M letter size at 2 meters. What's your acuity there? 2/10M. Exactly right. So we don't do any conversions or anything like that. Everything will be made up, and you can see how the optotype changes if you convert it to Snellen. We don't convert any of the M acuities. So as I mentioned before, with the ETDRS and the Bailey-Levy chart, each line decreases in size by 0.1 logmar. Now, each line has 5 letters on it. And if you take 1 and you divide it by 5, you get 0.02, as you can see here. That means that every letter on a line is worth 0.02 logmar. What we previously talked about with Snellen was that as we that patient that we saw before that sort of hopscotched their way down the chart, we all had disagreements on what kind of acuity that we would record, right? Remember that just a few minutes ago? Okay. So in this case, if we state because of logarithmic progression of the letters down the chart, what we can do is we can just state each letter is worth the same amount. It doesn't matter necessarily on which line it is, but each letter is worth the same amount, and therefore we can either, 1, consolidate all the letters and just say, oh, the patient read 35 letters total, even though they missed some as they were on their way down the chart, or we can do a mathematical function that we'll see here in just a second in order to determine their exact precise visual acuity. And this is kind of what I was talking about. What if a patient misses letters, that sort of thing. So what we can do, I say this, that we can eliminate plus or minus, that sort of thing. That's a little bit wrong. Let me explain here. So with Snellen, we didn't have any way to rectify the letters that were missed because it's not a logarithmic progression as you make your way down the chart. The 2200 line, and then it jumps down to a 2100 line. And so from a logmar progression standpoint, that's much different. It's not 0.1. It's not that uniform progression down the chart. And so we can't say, well, each letter is worth the same value because they're not. Some letters, obviously the letters are bigger than one another, but the progression in decreasing letter size is not the same as you work way down the chart. And therefore, different letters are worth different amounts. So we can't do the kind of math that we're fixing to do on a Snellen chart. Now, these days, what we do, back in the day, we had a type of EHR called CompuLink. And the low vision doctor that was here was able to work with them in order to create some little applet where all you had to do is punch in the numbers of letters that the patient got right and the distance that the chart was at, and it would spit you out a logmar visual acuity or a Snellen acuity based on the logmar that the patient was able to achieve. These days, it seems cruel to make you do this in clinic by hand. And so what I typically do is say, consolidate all the letters. If your patient hopscotched their way down the chart, got 3 letters here, 4 letters here, 2 letters here, something like that, and you get to like 23 letters at the end, then you can just say, you can go 5, 10, 15, 20, and then, you know, whatever acuity that is, +3, or the next line down, -2, something like that. But the point is that I'm trying to make is it's much more accurate to do it that way because each letter is worth the same amount, so you can just consolidate it. Rather than kind of going, well, they missed a letter here, they missed a letter there, we can't rectify that in any way, mathematically at least. Let's work through the math real quick here. And then I think that'll be a little easier to understand. So to find a very precise visual acuity, instead of saying, you know, 20/25 or 4/20m +2 or -3 or whatever, what you can do is you can find a very exact acuity by setting up your chart and then counting the number of letters that the patient reads beyond the top line. So with our charts, unfortunately, they're older style. They're still calibrated for 4 meters. But at that distance, at the 2200 line on the top or a 40M letter on the top, and at 4 meters, then the logmar equivalent of that is 1.0. So each, that entire line, if the patient reads the entire line and that's it, then their visual acuity would be equivalent to 1.0 logmar. Now, the thing that you know about logmar is the smaller the number, the better the acuity, right? And if it goes into negative territory, that indicates what? Better than 20/20, exactly right. So as we work our way down the chart, we're decreasing 1.0, that logmar from the first line, we're decreasing it by 0.02 for each letter that they get correct. So as we work our way down the chart, we count up the number of letters that the patient gets correctly, and as long as they got all the letters right on the top line, a 1.0 logmar in this case, then we just subtract that final number, multiply it by 0.02 and subtract that final number from 1.0. Now I thought we would have a whiteboard in here, and well, we can work some of these in lab perhaps, but not sure how to record and get that information here. But just let me know if this is confusing and I can work some out by hand, and maybe I'll grab the whiteboard for lab or tomorrow or something like that. But let's just start here, okay? So let's say that our chart is calibrated such that the top line is 2200 equivalent, and our chart is at 4 meters. Let's just think back in the day whenever it was at the old NSU, charts were 4 meters away. So the MAR of a 2200 optotype, whenever it's set all the way out there at this 4 meter test distance, was a 10. So the MAR was a 10, and therefore the log MAR of that, where you just take and use your calculator, and you type in 10 and you press log, and it'll spit you out a 1.0. So that's our starting point. As long as the patient got all 5 letters on the top line correct, you just start off with 1.0. Now, the patient read 36 letters past that point. So not including that top line, not including those 5 optotypes on the very top line, they read 36 more letters. So their total letter count was actually 41. But we don't count that top line. And so we said, in this case, the patient read 36 letters beyond 2200. Because each letter is worth the same amount, 0.02, we can multiply the 36 times 0.02 and come up with a 0.72 value. Now this number doesn't necessarily mean anything, but it's going to get us to the logmar. And we take 1 and we subtract 0.72 from 1 in order to get 0.28. So now we're going to take a 10 to the 0.28, and this is going to give us our MAR. And so if you've got your calculator, if you've got your phone, or even on your computer, you can do this math. But once you take this 10 to the 0.28, it's going to give you this 1.9 mar. And then all you have to do to get Snellen equivalent from that is multiply 1.9 times 20, and that will give you 38. And so the patient's acuity in this case, the exact precise acuity is going to be 20 over 38.1. Now let me go on to this next chart real quick and see if I can see where what that shows. I can't see that there, but we'll come back here in just a second. What I want to tell you real fast is you can see how if the patient had read 35 letters, perhaps their equivalent, their Snellen acuity would have been something like 2040 in that case. But because they read 36, it's one more letter indicating that their acuity is slightly better than 2040. And so in this case, their acuity is 20 over 38. This isn't something that's available in the drop-down menus on Revolution, which is one reason why I've kind of quit asking students to calculate this precise logmar acuity, and instead have said try to consolidate and count up the number of letters correct. And let me show you what I mean here real quick. So based on what we've previously talked about, patient got all 5 letters correct on the top here, and so we're starting off with a base of a logmar of 1.0. So we don't have to worry about anything from there. Logmar of 1.0. And now we count the number of letters that the patient got right. 4, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Let's see here. Let me pull up my calculator. So we're going to take the letters that they got correct beyond the 1.0, right? On the first line. So you're going to take 16 times 0.02. And that's going to give you 0.32. You're going to subtract this from 1.0. Okay.
0.68.
0.68, yep. And now you're going to do the 10 to the 0.68. And this is going to give you your mar. And so in this case, it's going to be 4.78 is what I pulled up on my calculator here. So that's your mar. In order to find the actual Snellen optotype size, you would multiply that times 20. And so this would be equivalent to 20 over 95. Again, not something that you're going to see in a drop-down menu on Revolution. You could, of course, put it in the notes section, which is what we typically do just to make it easier and not have to try to find it. The other thing, how many letters? What did I say? 4, 8, 16. Thank you. So what you could say in this case is patient read 16 letters beyond the top line. So you go 5, 10, 15 plus 1. And so we could consolidate all of it and say all of these X's, move them here. And so we would be 5, 10, 15 plus 1. We would be on this line right here, or this line right here plus 1. And that's how you could also do it. Because each letter is worth the same amount, we can consolidate. We don't have to worry about, you know, I think this is 100-foot letter over here. It doesn't have M. 100 plus 2 minus plus 3 minus 2, something like that. We'll do some examples in lab and everything too. So I'll figure out how to work this online. Yes, just
So how many are you counting that, is it 29? Or how many are you counting that they missed? Or is it the ones that I got?
it's the ones that they got. So the ones that they get correct, you subtract, you multiply that number times 0.02. Yeah. But don't forget, we don't count this top line. As long as they got all 5 correct, then we don't count it. If they miss one, then their sort of base number that you would start off with would be like 1.02 in this case. You can rectify that if a patient misses a letter or 2 on the top line, but then goes on to do very well on the rest of the test, just by adding on those letters that they miss.
But the correction factor would be in the, basically that's what the second step is for, 1 minus.
Yes,
there.
exactly right.
That's the correction
Yeah,
factor.
that's the correct. That's to account for that 2200 or that top line, that 1.0 log line. We're going to do examples of this. I expected to have the whiteboard today, so I wasn't prepared, but I'll try to make sure it's here for tomorrow. So as I mentioned before, if a patient missed these optotypes and you were just to ask a clinician based on their Snellen acuity knowledge, you would likely get lots of different responses on how you would record a patient's visual acuity. On a side note, based on the losses or based on the misses that the patient the letters the patient missed on their way down the chart, what might this indicate? So is that what, okay, I heard a little bit of, I thought I heard that, yeah. So it could potentially indicate some sort of visual field loss, maybe a hemianopsia, something like that. So bookmark this, put a star on it, something like that. This is how we typically record acuities because we do have slightly different charts in each clinic, unfortunately. But here in Tahlequah, we use traditional ETDRS. Broken Arrow, we have an Acuity Pro, and we'll talk more about that when or if you guys go to Broken Arrow. School for the Blind, also ETDRS, but the chart is a 3-meter chart, which these days, considering our shorter exam lanes, we may need to consider getting some updated charts, just like School for the Blind. Remember, calibration, calibrated for 3 meters. All that means is that if the chart is set at 3 meters, you can use the Snellen equivalent over on the side. But don't worry about that at all. Just use the M acuities. So this is sort of a pro tip, or if you think about it at some point in the future, you have a patient that walks in the door and you can see what their base acuity is before they even get in, then you can set the chart at the appropriate distance without having to sort of hunt or figure out or start at 3 meters and then move it to 1.5 and then move it to 1 or whatever. So this would just be like, oh, the patient came in and their acuity at their last appointment was 2400. So move the chart up, have the distance, and that'll make it to where you can get much more accurate acuities much quicker than having to sit there and have the patient struggle for 4 or 5 minutes only to then have the distance of the chart. So again, this is considered a pro tip. You might bookmark it and put a star on it. Not anything you're going to be tested over per se, but just something to help you out in clinic. The other thing, something that students often forget, we want to make sure that the patient reads down into at least that second line. And so if you look back at the ETDRS chart, we want to get them into the chart far enough to where we get the crowding phenomenon. If all they read is the top line, have the distance and go again. We want to get them into the chart so that they are crowded, they get some crowding. Therefore, we know that those acuities are accurate. Just a couple of other things. Make sure that you leave the room lights on, and the cabinets have lights in them. And so make sure that they're turned on, plugged in and turned on as well, where applicable. So let's talk about some more portable charts. You all have a Leia numbers chart, is that correct? Yeah. Okay, excellent. So Leia numbers chart is sort of the standard anymore that we use here at the school. There also is another portable chart called the Feinbloom chart, which was sort of our standard for a long, long period of time. So with Leia or Feinbloom, they have both, they have optotypes labeled in both foot letter and M acuity, but it's basically the same as we've already talked about. Now, one thing to note, and I say it, down here at the bottom, you don't want to mix units. So if your test distance is at 10 feet, then don't put an M acuity optotype there. Put a foot letter acuity optotype. If your test distance is at 2 meters, then you want to use M acuity. So you don't want to mix your feet, or you don't want to mix your units up on your chart. And other examples there are just how you would record, depending upon if you use foot letter or if you use M acuities. So this chart, you could probably see it a little bit better on your computer. I think it's a 160 optotype size. And so I think I've got an example here, but just know that whatever distance that you use, if it was in feet, then you would use the test distance over the optotype size, which is 160 or whatever that is right there. So know that with Leia numbers and with Feinbloom, it was traditionally measured in foot letter size. But now, since the charts include M acuities, you can do whatever you want. As long as you don't mix the units, whatever units you want to use is fine with me. So let's say, for instance, it's 100. Sorry, that's my fault. We need to get some better resolution pictures, I guess. So let's say that the test distance was 5 feet and your patient read a 100 foot letter. How would you record this acuity? 5 over 100 foot letter, exactly right. And I do want you to try to use that designation. Units are important just to make sure that the person next in line knows what units you were using. So 5 over 100 feet or foot letter would be what I would recommend recording. Let's say that now the test distance is at 4 meters and the patient read the 48M optotype. Since we don't mix our units, how would you record that acuity?
48M.
Perfect, exactly right. Okay. So I think we're out of time at this point, and we'll pick up here with Fine Bloom, in our next, I guess.